This video is submitted as supplementary material for the IJRR submission titled 6R Cuspidal Robots, Kinematic Issues and Guidelines for Path Planning and Deciding Cuspidality. In this video, we show different types of paths that can occur for cuspidal robots by taking an example of a commercial cuspidal robot. So we present different types of path while following a given closed path in the workspace of a cuspidal robot. The different types of paths are the infeasible paths, the continuous and repeatable path, the non-singular change of solutions that are non-repeatable paths, and the non-singular change of solutions that correspond to repeatable paths. This is the robot by Kinova Robotics named Jaco Gen 2 6 degrees of freedom robot. It is a non-spherical wrist. Notice the DH parameters on the right hand side, especially the value of D3, A5 as well as alpha 4 and alpha 5. Generally, the value of D3 is either 0 or equal to D2. The non-zero value of A5 means there is an offset in the wrist, and thus the inverse kinematics model is no more decoupled for the orientation and translational analysis. Also notice the value of alpha 4 and alpha 5 is 55 degrees, contrary to most of the other industrial robots which either have parallel arrangements or perpendicular arrangements, meaning alpha is either 0 or 90. We study the slice of the Jaco Gen 2 robot, especially the zoomed slice. Here every color denotes different number of inverse kinematic solution. So the region that is shown in green color has 8 inverse kinematic solution, the purple region has 6 and the yellow region has 4 inverse kinematic solution. We are interested to study this particular path that crosses different regions of varying number of inverse kinematic solutions in the workspace. In order to study this path, we plot the progress of path with respect to the theta 3 value of each inverse kinematic solution. So the path is discretized in several points, and at each point the inverse kinematic solution is solved algebraically, and you can see that the blue points, they correspond to the solutions for whom the value of determinant of Jacobian is greater than 0, while the red colored points correspond to those inverse kinematic solution whose determinant of Jacobian is negative. We here are showing different important points along the path, such as when we cross the regions and as well as the vertex of the path. Notice here that as we are performing a loop in the workspace, it is expected that the initial inverse kinematic solution matches the final inverse kinematic solution, as is clear from this particular graph. Now we want to study the different types of paths that occur while following this given closed loop in the workspace. As we start from the green region, we have 8 different options to follow this particular closed path. They are defined as Tn1 to Tn4 and Tp1 to Tp4. The Tn are the trajectories with a negative value of determinant, and the Tp trajectories are the trajectories with a positive value of the determinant of Jacobian. So let's start our path which corresponds to Tp4. So here we can follow the loop smoothly till a particular point. So we can follow it till we exit the green color region and enter into the purple region. At this point, we are entering in the region of 6 solution region from 8 inverse kinematic solution region. So we have lost 2 inverse kinematic solution. We do not have a continuous path beyond this point, and I can jump. It is possible to jump to some another path in the same aspect in a non-singular fashion. It is very important to note that this cannot happen for any non-cuspidal robot. Similar situation happens in Tn1 when we are exiting the purple region and entering the yellow region. So we further lose 2 inverse kinematic solution, and similar issues can happen where we will see the sudden jump to Tp2 or Tp3, and this jump is completely non-singular. We never cross singularities in these transitions. Trajectories corresponding to TP2 and TP3, they lead to continuous and repeatable paths. They are repeatable paths because of a particular reason that we will be discussing soon. At this particular point, we are entering the green region from yellow region and we are gaining 4 inverse kinematic solution, which is never a problem. This path can be repeated because the trajectory ends with the same inverse kinematic solution that it started with, and so we can continuously repeat the path as much as we want. But this is not always the case in cuspidal robots. Take an example of a path in the aspect where the determinant of Jacobian is negative. So the Tn path is a continuous path and there is absolutely no problem in following the loop. But notice that we are completing a loop and coming in a different joint configuration, and this path is not repeatable because the end of this path corresponds to a starting path which cannot lead to a continuous path for following the closed loop. Such non-singular change of solutions are a property of cuspidal robots and by definition cannot happen in non-cuspidal robots. But are all non-singular change of solutions not repeatable? Well, that's not true. In fact, here we show an illustration where there is a non-singular change of solution which indeed is repeatable. This happens due to a special case where the end inverse kinematic solution of the path matches to another path which then is a non-singular solution whose final inverse kinematic solution matches the initial inverse kinematic solution of the path we started from. So for example, this particular path we can continuously repeat the closed path, but every time we will start from a different configuration and end at a different configuration.